Welcome back. In this lecture, we're going to learn about another architectural style and pattern, which is called event-driven architecture. First, we will get an introduction to what event-driven architecture is, and later we will learn about all its benefits, as well as use cases where this type of architecture can be very powerful and useful. So what is an event-driven architecture, and what are its main components? If we recall from the lecture about microservices, if microservice A wants to communicate with microservice B, then not only microservice A needs to be aware of the existence of microservice B, but also it needs to know what API microservice B provides and how to call it. Also, at runtime, microservice A has to call microservice B synchronously and wait for its response. So, from what we just described, we can see that essentially microservice A has a dependency on microservice B. In an event-driven architecture, instead of direct messages that issue commands or requests that ask for data, we have only events. An event is an immutable statement of a fact or a change. For example, a user clicking on a digital ad or an item being added to a shopping cart can be thought of as fact events, while a player of a video game or an IoT device like a vacuum cleaner moving from one position to another can be thought of as change events. In an event-driven architecture, we have three components. On the sending side, we have the event emitters, which are also referred to as producers. On the receiving end, we have the event consumers, and in between, we have the event channel, which is essentially the message broker we learned about in a past lecture. When we use the event-driven architecture style with microservices, we can get a lot of very useful properties and benefits. For example, now if microservice A communicates with microservice B by producing events, the dependency of microservice A on microservice B is removed. In fact, microservice A doesn't need to know anything about the existence of microservice B. And once microservice A produces the event, it doesn't need to wait for any response from any consumer. Because services don't need to know about each other's existence or API, and all the messages are exchanged completely asynchronously, we can decouple microservices more effectively, which in turn provides our system with higher scalability, and we can add more services to the system without making any changes. For example, if we have a banking system, we can start with just two services. The first service is the front-end service, which simply provides the user with the user interface and takes in the user's input, such as money deposits, transfers between accounts, and so on. The second service is the account service, which maintains and updates the balance for each user. Now, if we use an event-driven architecture, then every action that the user performs on their account can be events that are produced by the front-end service. And the account service simply subscribes to those events so it can consume them and update the user's balance. Now, because we decouple those services using a message broker, we can easily add a mobile notification service which subscribes to the same channel. And every time a user makes changes to their account, this service can send push notifications to the user's mobile device about the activity in their account. Notice that adding the service was super easy and did not require us to make any changes to the front-end service. Later, we can just as easily add a fraud detection service, again without making any changes to the existing services. And similarly, we can add another producer service that can integrate with other third-party services. For example, it can integrate with utility companies that charge our clients automatically for gas, electricity, or water. Or we can integrate with payroll services that perform direct deposits to the client's account on behalf of the client's employer. And adding this producer will also not require us to make any changes to our system. In addition to the horizontal and organizational scalability, event-driven architecture allows us to analyze streams of data, detect patterns, and act upon them in real time. For example, the fraud detection service can detect suspicious activity in the user's account by looking at the stream of events that happen in the account in real time, without waiting for this data to be post-processed and stored in some database. For example, it can look at the recent transactions and notice that in the last hour, 2 transactions happened in stores and restaurants in Los Angeles, California, while one of the transactions happened in a remote location somewhere in a different state. The fraud detection service can easily detect the suspicious activity, which is possibly a result of someone stealing our user's credit card or account information and trying to make a purchase. Similarly, by analyzing a stream of transactions in real time, it can detect that 5 different transactions were made within a short amount of time, which simply cannot correlate with real human activity. This activity would be immediately flagged as fraudulent and would trigger the fraud detection service to communicate with the account service, which would freeze the user's account. And it would also communicate with the notification service, which would alert the user about the situation. When we store all the events that happen in our system inside a message broker, besides performing real-time analysis, we can also use this information to implement very powerful architectural patterns. One of those architectural patterns is called event sourcing. If we continue with the same example of the banking system and imagine what a hypothetical log of events for a particular user would look like, we can notice that essentially this event log represents all the transactions that happened in the user's account. And if we replay all those transactions from the beginning of time, we can arrive at the account balance that is currently stored in the account service database. So, by using the event sourcing pattern, instead of storing the current state in a database, we can simply store only the events, which can be replayed whenever we need to know the current state, and we eliminate the need for the database. Now, because events are immutable, we never modify them, and we simply append new events to the log as they come. By using this pattern, we can add another service that can generate a statement or look up any number of transactions that happened in our user's account simply by looking at the last n events in the log. And if our fraud detection service decided that one of those transactions was not approved by the customer, it can easily be fixed by adding another event into the log that compensates for it. And all of that without the need to freeze the user's account or modifying records in a database. For example, if the user was charged $100 by somebody who stole the user's credit card information, the fraud detection service can simply credit the user's account with $100. And all of that information will be reflected in the user's statement immediately. Using the event sourcing pattern, we can choose to store those events for as long as we want and allow the user to look back at his transactions from 5 or even 10 years ago. But we can also make our querying faster by adding snapshot events, let's say every month, that summarizes everything that happened until that point of time. Another very powerful architectural pattern that we can implement using event-driven architecture is called CQRS. CQRS stands for Command Query Responsibility Segregation. This pattern can solve 2 problems for us. The first problem is optimizing a database that has a high load of both read and update operations. When we have a database that has a high load of both read and update operations, concurrent operations to the same records or tables contend with each other, making all the operations very slow. Additionally, if we use a distributed database, generally we can optimize it only for one type of operation at the expense of the other. For example, if we have a read-intensive workload, we can compromise on slower writes. Or if we have a write-intensive workload, we can compromise on the performance of read operations. However, in the case when both operations are equally frequent, we have a problem. The CQRS architectural pattern allows us to separate update and read operations into separate databases, sitting behind two separate services. In this case, service A would take all the update operations and perform those updates in its own database where it optimally stores the data for such updates. But additionally, every time an update operation is performed, it also publishes an event into a message broker. Meanwhile, service B subscribes to those update events and applies all those changes in its own read-optimized database. And now all the read operations will only go to service B. Now both update and read operations can go to two separate services without interfering with each other, and the data in each service is stored in an optimized way for each type of operation. The second problem that CQRS architectural pattern helps us solve is joining multiple tables that are located in separate databases that belong to different microservices. Before we split our monolithic application into microservices, we had all the data tables inside one single database. If that was a relational database, we could easily and relatively quickly combine and analyze records from multiple tables by simply using the SQL join operation. However, once we migrate to microservices architecture and follow the best practice of having a separate database for each microservice, those join operations are a lot harder. Now we need to send a request to each service separately, which is a lot slower. And then we also need to combine this data programmatically, because now we potentially have different types of databases, some of which may not even be relational databases. So CQRS solves exactly that problem. Now, every time there is a change in the data stored in service A or service B databases, those services would also publish those changes as events to which service C subscribes. Meanwhile, service C stores what's called a materialized view of the joined, ready-to-query data from both service A and service B in its own read-only database. And now, whenever we need to get a joined view, we don't need to send a request to two different services. Instead, we need to send a request to service C only, which already has the data ready for us. Now, let's demonstrate both of those use cases for CQRS pattern in a real-life example. Let's assume that we have an online store where we have hundreds of thousands of products and we have millions of users who search for and leave reviews for those products daily. So if we use the microservices architecture, we would have the product service that has its own database. That database contains things like the product's name, their inventory count, description, price, and so on. We would also have the review service, which manages and stores all the reviews for all those products. So, as we can imagine, reviews are coming to our system constantly, so updates to the reviews database are very frequent. Similarly, our product's inventory keeps changing as people purchase products or additional products are added and updated. But we also need to read and combine the product's information and their reviews information very quickly and frequently, because users constantly search for products and want to see both their description and prices, which would come from the product service, and also see each product's reviews and rating, which we would need to get from the review service. So to solve this problem, we can use the CQRS architectural pattern. By using this pattern, we can add the product search service, which would have its own database. This database would store all the necessary combined data for each product and its reviews. And the service would also subscribe to updates to this data from the review service and the product service. So now, a user who wants to search for a vacuum cleaner or maybe a pair of shoes can get a page with all the potential results very quickly by sending a request only to the product search service. And if the user wants to sort by or filter by the number of reviews or rating, it can also be done very easily and quickly. In this lecture, we learned about the event-driven architecture. We learned about a few benefits that this type of architecture provides to us, especially when combined with the microservices architecture. A few of those benefits include decoupling microservices, which provides us with higher horizontal and organizational scalability. Additionally, event-driven architecture allows us to analyze and respond to large streams of data in real time. We also learned about two very useful and powerful architectural patterns within event-driven architecture. The first one was event sourcing, which allowed us to store and audit the current state of a business entity by only appending immutable events and replaying them when we need to. And the second architectural pattern was CQRS, which allowed us to optimize our database for both update and read operations by completely splitting the operations to different services. This pattern also allowed us to quickly and efficiently join data from completely different services and databases. I hope you learned a lot in this lecture, and I will see you all very soon.